Hey guys, welcome. This is an intro being recorded for Advent of Code 2022, day 17. I recorded an intro right before I recorded day 17, which is now a couple days ago, but I recorded it without any audio. So I'm recording this. I just want to say thank you guys for watching, and we're getting started with day 17. Let's go. Get us into the right mode. All right, here we go. And let's kick off. Day 17. Let's go. Pyroclastic flow. All right, we get some lava flow. The handheld device located alternative exit from the cave. You and the elephants. The ground is rumbling almost continuously now, but the strange valve bought you some time. It's definitely getting warmer in here, though. The tunnels eventually open into a tall, narrow chamber. Large, oddly shaped rocks falling into the chamber from above, presumably due to all the rumbling. If you can't work out where the rocks will fall next, you might be crushed. 5 types of rocks of peculiar shapes where pound is a rock and dot is an empty space. Okay, these look like Tetris pieces, all right? The rocks fall in order shown above. First the dash shape, then the plus shape, then the backwards L shape, and so on. Once the end of the list is reached, the same order repeats. Okay, so these fall over and over and over again. The rocks don't spin, but they do get pushed around by jets of hot gas coming out of the walls themselves. A quick scan reveals the effect of the hot gas will have on the rocks as they fall. Our puzzle input. Woo. Oh, so these shapes are the ones that always fall. Okay. And our input is the jet patterns. Left arrow means a push to the left, and right arrow means a push to the right. Pattern will push a falling rock right, then right, then right, then left, then left, then left, and so on until the end of the list is reached. The tall vertical chamber is exactly 7 units wide. Each rock appears so that its left edge is 2 units away from the left wall, and the bottom edge is 3 units above the highest rock in the room, the floor. If there isn't one, after the rock appears, it alternates between being pushed by a jet of hot gas 1 unit and then falling down 1 unit. If any movement would cause the part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused the falling rock to move into the floor or an already fallen rock, then the falling rock stops where it is, having landed on something, and a new rock immediately begins falling. So yeah, we're just playing Tetris here. Cool, so we just have to write a Tetris game. Cool. All right, let's read in. Let's get our input, read in everything, start writing some code. Prove the elephants your simulation is accurate. They want to know how tall the tower will get after 2,022 rocks have stopped, but before the 2023rd rock begins falling. Wait, hold on a second. How high do they start, right? Doesn't that... I guess that's my question. Is... Okay, so they're always starting with at least 3. So when a new rock begins falling, it starts centered on the center of the 7 unit wide and having 3 empty rows until the first rock. So because the first rock went right, left, it gets put there, and then there's a left, right, left, right. And a new rock begins falling. Cool. Okay. And they always start with 3 units of space. Cool. All right, so I believe we can just implement the game or the simulation exactly. Maybe we can do some sort of looping thing for the part 2. Okay. Let's read in the input. Long input. All right, in the example we're given is the second looping of the 6 rocks, so that's like 12 rocks, right? Okay. All right, let's do rocks. Rock is a matrix of stir. The tower is represented by the highest. We can actually represent the tower instead of representing the full shape of the tower, because that could get really big. We can just represent the tower by the highest rock, or sorry, in each space. So that's just 7 ints. So that's tower equals list of int 7, length 7. Okay. So it starts out as 0. So initial tower equals 0, 0, 0, 0, 0, 0, 0. And then the different rock shapes. I'm actually gonna make the rock shapes each 7 wide. So rock shape, rocks equals a list of rock. And we're gonna go with four wide. So the first one is dot, 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 pound, 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 dot. And then second one is directly centered, so it's dot, 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 pound, dot, 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 and dot, dot, pound, 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 dot, 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 pound, dot, dot, dot. Third one is an L, dot, 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 pound, dot, 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 pound, dot, dot, pound, 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 dot, dot. And we have 1, 2, pound, pound, dot, 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 dot. And we have that x4 for I in range 4. All right, so that one pretty simple. And finally, the dot, dot, pound, pound, dot, dot, dot for range 2. And then the last one is the flat. Dot, dot, pound, 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 dot. Okay. Wait. Oh, that's the first one again. And this should be 6. 1, 2, 3, 4. No, it's only 5. 1, 2, 3. Okay, so there's only 5. All right, got it. So we got the list of our rocks. And we have a representation for our tower. Now we just need to read in our input, which is a single line of arrows. Okay, so we just read it in as arrows. And we can start going with our simulation. So what represents the state of this problem? State 1 is going to be tower, which is a tower. So the tower state, like what are the highest points? And then the next rock, which is an int representation of these, like a integer, so index into this rock. Okay, so state equals state 1 of tower equals initial tower, and next rock equals 0. And then for state, so for I in range 2022, we're just going to run state dot simulate next rock. It's going to return a new state, and then we're going to return max of state.tower. So that's it. So now we just have to write a simulate rock. So def simulate next rock, self, returns a state 1. Okay. So rock shape. So the rock equals self equals rocks self dot next rock. And we'll just say new tower equals tower, and we'll do some stuff, do stuff here, and then we'll return state 1 tower equals new tower, next rock equals next rock, self dot next rock plus 1 mod len of rocks. All right, so we got our return value. Now we just have to simulate each fall. So let's think about this a little bit more directly, because it's the only thing we have left. So the rock starts. Oh, we also have the input, of course, right? We have the arrows. And whenever you pop off an arrow, so right, and then arrows equals input dot arrows. Okay. Okay, so we start with the rock being above 3 units above the highest tower. So highest point equals max new tower. So we start with, so the rock shape falls 3 units before hitting the highest point. So we basically have to think about how the rocks will move. So what if rock so for 3 iterations, we're just going to move it right and left and not test down below. So let's do while true, try moving with arrow. So arrow, comma, arrows equals arrows 0, arrows 1, colon. And then if arrow is left, then we have to move it left. So I'm gonna change this definition of rock to be each row being a tuple of how wide, of where the rocks are. So this rock is going to be 0, 1, 2 to 6. In an array, right? So it's one row from 2 to 6. This rock is going to be 3 to 4, 2 to 5, 3 to 4. 4 to 5, 4 to 5, and 2 to 5. Two to 3. And 2 to 4. Okay, so we've now changed our definition of rock to be just tuples of indices. And so we can move those tuples around. So rock equals shift rock left. All right, so let's make a def shift rock. Rock left equals false, down equals false, right equals false. We'll do shift rock just left or right. If left, then we just have to check if any rock is already at 0. So if min of line 0 for line in rock is equal to 0, we don't move, return rock. Else we do return line 0 minus 1, line 1 minus 1 for line in rock. Else, so if right, we just have to check if the max is 6. And do a +1 here. All right, so now we shifted. So now we know how to shift rock left and right. So, and we just need to check. Now we need to do def shift rock. So descend rock or drop, we'll call it drop rock, and then we need the tower. So we just need to see if any section of, we need to know like what level we're starting at. So the lowest rock level, rock level. So the tower is going to be, let's say, so the tower here is zeros, all zeros, and the rock level here is 1, 2, 3, 4. And then we decide to drop it, and so we're going to set the rock level to 3. And so we just have to check if the lowest level of the rock is the last line of rock. So for I in lowest line, for we'll call it column, if that intersects with any rock. If rock level is less than or equal to tower at that column, return rock. We need to return a new tower. True, and we need to construct a new tower. All right, so we just need to construct new tower here. So I'm going to skip that for now. And if the rock level is less than or equal to, we'll just return false, like we couldn't, or none, because we couldn't drop the rock. Else return true. Okay. Can drop rock. Okay. Try moving with the arrow here, and then we say if can drop rock, self.tower and I guess the highest point is going to be the rock level starts at the max of the tower plus 4. Rock level minus equals 1. Else, then this is where we stop. So then we add everything up. The question is, do we ever need to test like, is this correct? And I'm realizing it's not, because specifically for this rock. Oh, and also we need to do shifting with the tower, right? Yeah. So Let's make a function that says intersects tower. Def intersects tower. Rock, tower, rock, level. So for row level, or for I row in rock, ::1. So we're going to go up the rock. Level equals rock level plus I. So because we're going up the rock, we can increase the level. And then for column in row, in range of row, right? Because remember, these are tuples. The tower, if well, now I'm thinking this tower representation won't work. We might have to exactly draw the tower. All right, let's exactly draw the tower. The reason we might have to exactly draw the tower is like, what if somehow you could place this thing like below here, and like you have to just know what every tower is. So the tower is now so let's just represent everything as a list of bool. So a row, like 7, all right, and then these rocks will change to Okay, we converted all our rocks. And now we have our tower. Okay, so we converted shift rock. Okay. So for row in reverse rock, our level equals rock level plus I. For column in row, okay. All right, so if column and tower of at level so if they both intersect, return true. So if both column and tower at that level, at that column are true, then we return true. And that's just how you do it. And otherwise, you return false. So now we have def try shift rock tower left equals false. Rock equals try equals shift rock. Rock left. If intersects tower rock next rock tower rock level then return none. Right. Else return next rock. Okay, so that's how these functions will work. So we're going to have a try drop rock as well. Try drop rock. And so it's just going to be if intersects tower rock tower rock level -1 return none, else return rock level. And then finally we need to update tower def land rock tower rock level So if we determine that this rock can't move anymore because one of these two functions, because this try drop rock return none, then we change the tower. So what we have to do is just need to do something like this. Tower at level equals row j or tower level j for j in range 7. So basically we take the or of the two, right? Because no trues can ever coincide, and we just put them together. And the only thing we have to worry about is tower that long. So if len of tower is equal to level tower plus equals an empty we just add another level to the tower, and that way we can set it. And then we also should try, we also just need to do this. So if level is greater than or equal to len of tower, then we just pass, like we don't care, because it'll never return true in here. So the tower just doesn't exist at that level. Okay, cool. So now we have all our functions. So we're going to do try shift rock. And actually try shift rock, I don't care if it returns none. I just need it to return the rock, because I don't care like what happens if you try to shift it left or right, because you still try to drop it. Cool. So that is try shift rock is rock tower rock level left. And then we try dropping. So drop rock equals try drop rock, and this is rock self.tower rock level, new rock level. This is just a true and a false. It's going to make it cleaner. If can drop rock. So if we can drop the rock, then the rock level minus equals 1. Else new tower equals land rock self.tower rock level. And we break, right? Because we got to simulate, we just return actually out of this function, because this is only simulating a single rock, right? So now we return state 1. Well, we can just break out of the while true, and that will increment the rock, give us a new, we have the new tower, we have the new arrows. Cool. Otherwise, we go back again, and now that the rock level has been dropped 1. Okay. Cool. All right. Yeah, and let's have a tower print tower. def print row. Return okay, and then print def print space, do tower, okay, then let me just print tower next rock, rocks next rock, self, print tower, doesn't matter, we'll just print the tower, self.tower. Okay. And then, so for the example, let's just run it. Times equals 2022 if len of input dot arrows is greater than, I don't know, 1,000. Else, how many do we want to do for the example? Let's just start with 1. Print state. Oh, and the max tower is the highest point on the tower, right? So it's the length of the tower. -1. Okay, let's try it. Oh, the max here. One, 2, 3, 4. So 0, 1, 2, 3, 4, which is 1 plus 3. Okay. Oh, the print tower needs to go up from the bottom, right? Okay, let's go to 2. All right, so is that what we got? That is what we got. Okay, let's go to 5. Okay, that's exactly right. Cool. All right, let's run it on the real input. Do the arrows repeat? In the end of the list, it repeats. Okay, we didn't simulate that. So okay. The next arrow is next arrow equals self.next arrow, and arrow equals arrow self.arrows next arrow, and then next arrow equals next arrow plus 1 modulus len of self.arrows. Okay. And then next arrow equals next arrow. Okay. Next arrow equals 0. We only really care about the tower. Is that everything? Yeah, should be everything, right? Okay, still working for the example. It says 3127. That's the right answer. Okay, so we simulated this problem. It was a little tedious, but we did it. That was good. Part 2. The elephants are not impressed by the simulation. The demand helped knowing how tall the tower would be after some giant number. Okay. 1, 2, 3 million, billion, trillion. 1 trillion. After 1 trillion rocks have stopped. Only then will they feel confident to proceed through the cave. Well, I suppose we have to find a repeating pattern, right? Like, all right, let's print. Let's try and see if we can find a pattern, just manually. 2856. Okay. Okay, tower. For I in range, tower, len of tower minus n. Look for a pattern. We're just going to look for this last 5 slots on tower over again. If tower I to I plus n equals pattern, print found pattern at I, print searching for pattern, print tower pattern. Okay, and then we're going to do search for patterns, state.tower. Because we have to search for patterns. We can't simulate, you know, a trillion things, right? Found pattern at 500. Oh, okay, that's interesting. So they found that pattern was found at 500 and at the end, right? So let's just stop this. 503, 1, 2, 3, right? Let's do 10. Ah, we do have a pattern, which means it will repeat. So it looks like the pattern is exactly 3123 minus 500. So, okay. So 3118 minus 495. So 3118 minus 495. So that's the repetition cycle. So cycle length equals this. And so target is 1 trillion. Just copy this number. Don't want to get this wrong. Okay. So how many drops are there between 500 and 495, right? That's the question. Is right, because like how many towers? So if if state dot len of state dot tower minus 1 is between 490 and 500, print I height len of state dot tower minus 1. Or it's 3113 less than state len of state dot tower minus 1 less than 3123. Okay, so 494 at rock 31. Well, it doesn't really matter. 315 491. 2015 3114. height 496. So it increments by 3 and then by 2 and then by 2. 3 2 2 2, with each rock. So we can just consider 315. So we have, we'll do this 491 to 3114, 491 to 3114. Rocks to cycle is 2015 minus 315, 2015 minus 315. So, and then the base height equals 491. So our target is after that many rocks. Oh, and then we need the base rocks. Base rocks is 315. So target minus base rocks divided by rocks to cycle. So cycles return base height times, this isn't cycle height, it's cycle length, it's cycle height, base height times cycle height, base height plus cycles times cycle height. Okay, and then we still have to simulate some more rocks, right? Or we have to be exactly on this, like after 100,000 rocks. So like we got to convert this to int. The leftover is going to be so yeah, we have to calculate a better cycle because we'll print leftover. So we still have 1,500 left over, right? So our cycle is like 1,900 long or 1,700 long. But maybe if we move back our cycle a bit to, yeah, so what is percent? So if we know it cycles every 1,700 rocks, then I want to look for a cycle that starts at rock 200. So if I minus 200 percent 1,700, I want to print it, and then doing this in part 2. Remove this from part 1. Okay. And then I want to cycle I want to hit this cycle more than one time. So we're going to do 200 plus 1,700 times 5. We'll do add 1 just to make sure. And let's see how this goes. Wait. Oh. All right. is there a pattern here? There is a pattern here. Yes, we proved that there's a pattern. Yes, 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 yes. Okay, so the height at 200 is 3432. So base, so height at 200 rocks is 3432. Cycle height is 2623, and cycle rocks is 1700. Base height, base rocks equals 200. Now we just remove these, and now we have target minus base rocks over rocks to cycle, with a leftovers going to be 0 because we proved that. And so we'll just call it, we called this cycle rocks, and that should, our second one to find, cool, whoops, cycle rocks. Nice. That's not the right answer. What? Answer's too high? Oh no. Okay. All right. All right. What did we do wrong? So we take a base height plus the number of cycles to reach the target times the cycle height. So 3432 at 200 rocks, and then every 1700 rocks it increments by 2623. Does it do the same thing for the example? Can we test it? It doesn't do the same thing for the example, not at the same cycle length. But I don't want to go solving the example. Yes, it's going to take a while. This will end in a second. All right, it's always 2623. All right, we are proving ourselves correct. So we just have something wrong with our calculation here. So base height 3432. All right, let's just do target for $200 plus 1700 times 2. 8678 at 3600. That makes sense. And if we did times 5, but when we do wait, we're off by 1. We have an off by 1 error. Oh, jeez. Okay. We gotta calculate over. We're off by exactly 1 rock. Because we checked when I is 200. But that's after the 201st rock falls. So I'm just gonna move this to before to run the state afterwards. So now it'll be, again, we're off by 1 in the correct area. So now let's rerun it. We're still 2623, but the base height is 1 down. Oh my gosh. 3431. Oh my gosh. There's our answer. No! Ah. Okay. Because I is 0 when no rocks have fallen, and I is 200 is 1 after 1 rock has fallen. So it's 200 after 200 rocks have fallen. And it's 1900 after 1900 rocks are fallen. I guess all we have to do is look at the example. Couldn't find an example. Oddly enough, the example cycles very quickly. Let's try again on the input with this search for the cycle. Yeah, there's our Yeah, there's our 2623 cycle height. Starting at 3423. Oh. It's still too high. All right, let's just start trying to guess them. So all right, so we want base guess is base height plus cycle height times I minus base rocks divided by cycle rocks. Cast int if guess not equal height print. Yeah, it's what we guessed before, right? Yeah, we've already guessed this. And it's too high. All right. Well, I got to go for a run. So I'm going to have to call this one here. I think we have the right way to do it, where we're determining that there's a cycle in the pattern. But for some reason, the math isn't working out, and that is disconcerting. We're even running through all these, calculating the state and determining that our guess is correct for every 1,700 rocks after 200 rocks. Wait a second. After 200 rocks, we have a height of 3431, and then every 1,700 rocks, we only add 2623. Is that math? That math doesn't work. Huh. I guess my question is, why is the height so high after 200 rocks? There's definitely a pattern. Wait a second. That's why it's... Okay. Another mutability bug. All right, so what happened? We modified the tower. In fact, we modified the initial tower during our simulation. I didn't mean to do that, but we did. Row for row in initial tower. And then when we searched for this base height, we started with something super high, and I didn't notice it until a while, but like you're only adding about 1.5 height per rock. So on average, like 2623 divided by 1700 is roughly 1.5. But then we had 15 for 200 to 3600. So, but the math kept working out. But yeah, another mutability bug hit us. But I'm really happy with like how we did it. Like we figured it out and kept solving it. And we definitely spotted the cycle really quickly. We just, our mutability bug got us. And I didn't even intend for this to happen because I kept copying to new towers. But unfortunately, arrays, have the append thing. We just should have done this at the beginning. So oh well, we did a good job. I'm going to upload this video now, and hope you guys enjoy it. And I'll be cutting together day 16 in a bit. So see you guys next time. Bye.